Assalamu alaikum to you all. So far in this series of online lectures, we have learned about trees generally, and we have learned in detail about two types of binary trees, namely binary search tree and AVL tree. In this lecture, we are going to learn another type of binary tree called binary heap. And this is the outline of the lecture. First, we learn what is binary heap, and then how do we represent it in a computer in our programs. Then we shall see how to use binary heap to implement priority queue. And then finally, we learn how to build a binary heap given a set of elements. Very much similar to the way we learn how to construct AVL tree and how to construct BST earlier if we are given list of elements. So this is our target for this lecture. Let's start with the first one. What is binary heap? A binary heap is a binary tree that has the following two properties. First, it is a complete tree. I'm sure you still recall how we define complete tree. It's a tree in which all levels are filled except possibly the last level. And even on that last level, the element that exists should be to the leftmost side. Right, so binary heap must be a complete tree. This is property number one. Property number two relates to the ordering of the elements. So actually binary heap is an ordered tree. And the order here is that the value in each node is greater or equal to the value of its two children. The value in each node is greater or equal to the value of its two children. So those are the two properties which, if they are satisfied, then a binary tree is said to be a binary heap. However, there are actually two types of binary heap. Max heap and min heap. The one we just defined above, especially concerning the second property, where we say the node must be greater or equal to the two children, is actually what is called max heap. That is, the parent is always greater. If you are to replace greater in the second property here with less, so the value in each node is less than or equal to the value stored in the children, then you have the other type of binary heap called min heap. So this is how you define a binary heap. It is a complete tree. Okay, so both the two cases, max heap and min heap, must satisfy property number one. It is a complete tree. And then if you are talking about max heap, it should satisfy property 2 with greater than. That is, the node should be greater than or equal to its two children. And if you are talking about min heap, then the node should be less than or equal to its two children. Let's take some example to see what this definition actually means. All the examples we are seeing here in figure A are valid max heap. Okay, they are all binary heap of the type max heap. So to know or to check whether a binary tree is max heap, we have to check the two properties. Obviously, all these trees, they are complete. Okay, so here the first level is full, The second level is not full, but the existing element is to the left. So this is a complete tree. The same thing here, level 1, level 2 are full, only the last level is not full, and the existing elements are to the left. So it is also a complete tree. And similarly here, both the two levels are filled, so it is a complete tree. So in all the three cases, property number 1 is satisfied. How about property number 2, especially with respect to max heap? Clearly here the node 15 is greater than the only one child here, 6. Okay, so this is a max heap. Here 10 is greater than both the two children 8 and 7. Okay, and 8 is greater than 2 and 3. 7 is greater than 6. So all the nodes satisfy property number 2 as well in this tree. So it is a max heap. The same thing here. There's only one parent here, 21, and it is greater than both its two children. So these are all valid max heap. Let's see examples of non-max heap. So again, all the figures here in figure B, all the trees in figure B are not max heap. None of them is a max heap. And the problem here is not the structure, because actually all of them are structurally correct in terms of complete tree. They are very similar to the trees we see above. So they satisfy property number 1, but they do not satisfy property number 2 for the max heap. You can see here 6 is less than 15, so this cannot be a max heap. Okay. Similarly here, although 10 is greater than 2 and 7, but 2 is less than 8 and 3. And similarly here, well, here is fine, 7 is greater than 6. So the problem is with the 2 here, rendering the whole tree to be not a max heap. Okay, similarly here, 12 is not greater than 21, even though it is greater than 10. So this tree is not a max heap. I should add, however, that this tree is in fact a mini heap, where you have the parent to be less than or equal to the children. It is called mini heap. So it is both satisfying property number 1, it is a complete tree, and the node here is less than its children or its one child. So it is a mini heap. What about here? It is not a mini heap either, because 12 is not less than 10. So this is neither a max heap nor a mini heap. The same thing can be said here. It is neither a max heap nor a mini heap. And the problem is not the structure, but the ordering of the elements. The last set of examples are also not max heap and not min heap as well. But the problem here is not the ordering, but the structure mainly. Actually, in this case, both. If you are looking at max heap, 6 should be bigger than 15. Okay, so since it is not a max heap. Is it a mini heap? Again, no, because this tree is not a complete tree. For complete tree, if some elements exist in a level, or if a level is not full, the missing ones should be to the right, but here the missing ones are to the left. So it's not a complete tree. So don't even bother looking at the ordering of the elements. Similarly here we have a gap in between. So it's not a complete tree. So don't even bother looking at the ordering of the element. This is neither mini heap nor max heap. So this is basically what is meant by a binary heap in general. and in particular the two types, max heap and min heap. There are 2 points to note while talking about what is binary heap. The first one is, if you probably have noticed in the examples, is that in binary heap, whether min heap or max heap, the ordering of the children is not important. Yani whether the left child is greater than the right child or the other way around is not important. As you can see, for example, here in this tree, the left child of 10, which is 8, is greater than the right child, 7. This is not a problem at all. We're not talking about BST or ABL. This is a completely different tree. And the only relationship we are concerned with is that of a parent and its 2 children. In the case of the max heap, the parent should be greater than both the 2 children, greater or equal to. So if you have 10, 10, 10, 10, 10, 10, it is still considered a valid max heap. Any duplicates are allowed in the binary heap, whether min heap or max heap. Okay, but the order of the children is not important. Here we have the other way around. Here the left is less than the right. That is fine as well. What is important is how do these 2 children compare to their parent. If the parent is greater or equal to both of them, then it is a max heap. If the parent is less than or equal to its 2 children, and that is true for all nodes, then it will be a min heap, and so on. So that is point number 1. Point number 2 is binary heap is generally not unique, actually for the same reason that we just mentioned in point number 1 above. Meaning if you have the same set of values, you can generate different heaps with the same set of values. Because we said the left and right, the ordering is not important. So because of that, we can have different trees with the same set of numbers. As you can see in this example from the book, figure 6.53, all these are valid max heaps created from the same set of numbers. Okay. Yeah, if you notice, the root is 10, but here the left child is 2 and the right child is 9. That is the children of 10, and so on. So you can get the different types of trees that are max heap with the same set of numbers. So don't expect to get a unique tree if you are given a set of numbers. Okay. So that's it about defining the tree itself, or what does it mean. The next question we need to answer is, how do we represent it in our program? So far, most of the data structures we have learned in this course, they are best implemented using link structure. For example, the BST, the AVL, the linked lists, stack and queues. Even though for stack and queue we saw implementation using array, we still concluded that the implementation using link structure was more efficient because of the memory issue related with array. However, this is an exception. It says here, binary heap is a dynamic data structure that is represented and manipulated more efficiently using an array. So for binary heap, it is represented actually using an array, not using a link structure. Although conceptually we should still draw it as a link structure with a root and left and right, but in reality, when we go to the implementation, it's going to be a simple normal array. Okay, so if it is going to be an array, how then do we store the elements? Okay, it says since heap is a perfectly balanced tree, its nodes can be stored in an array without any gap in breadth first order. So for example, if you have this list of numbers, okay, or if you have this heap, as you can see, this is a min heap, not a max heap. 13 is smaller than both 21 and 16. 21 is smaller than both 24 and 31, and so on. So this is a min heap, and also of course it is complete. It grows top to bottom, left to right. So this level is full, this is full, this is full, and the last level so far has 3 elements, and they are all to the left side. So it is a complete tree, and therefore it is a min heap. Now, how do you represent this min heap as an array? Just store the elements in breadth first order in your array. So the first element here, the root, will be in position 0. Then this is number 1. Then this is number 2, number 3, number 4, number 5, like that. Okay, so just store the elements top to bottom, left to right in the array according to their respective indexes. Yeah, so this is how we're going to represent it. And based on this representation, actually, there are some very interesting formulas that we're going to have, which are going to be very useful when we come to the implementation of the operations of binary heap, particularly the enqueue and dequeue, and later on when building the heap. Okay, the first point to note, if you are doing this representation where the first element goes to, where the root goes to index 0, then you can always get the root by simply accessing cell number 0. Okay, so this is the first formula. The root is always at index 0. The second interesting formula is that if you know the index of a child, if the index of a child is at I, then the index of its parent is going to be given by this formula. I minus 1 over 2 will give you the index of the parent. Let's take an example. Let's say 26. 26, assuming is a child node, its index is 8. Okay, suppose we want to know the index of the parent of 26 without looking at this tree, just knowing that the 26 itself is at index 8. Just apply this formula. So your I is 8, which is the index of the child. So 8 minus 1 is 7, and 7 slash 2 is 3. So the parent of this 26 is at index 3, which is 24. Now if you look at the tree, it is correct. 26 is having 24 as its parent. So just knowing the index of the child allow you to locate the parent. So if you take any element, this formula will always work. Knowing the index of a child, we can know the index of a parent. Okay, similarly, if we know the index of a parent, so it's the reverse condition now. Suppose a parent is at a certain index I. What will be the index of its left child, and what will be the index of its right child? So here we're talking about 2 elements, because a parent has 2 children, but a child has only 1 parent. So there's just one formula here. If you know the index of parent, if you know the index of a child, this is the index of a parent. But if you know the index of parent, you cannot say index of a child. No, you have to be specific. Index of which child, left or right? So the index of left child is 2i plus 1. So again, let's take an example. Randomly, suppose you take 24. Okay, 24 has index 3. So what will be the index of its left child? 2 times 3, which is 6, plus 1, 7. If you go to 7, you will see 65. So is 65 really the left child of 24? Look at the tree and you see that yes, it is indeed. Okay, 24 is having 65 as its left child. Similarly, if you know the index of a parent, you can know the index of its right child. Here is the formula, just 2i plus 2. So again, for the same 24, 3 times 2, 6, plus 2, 8. So at 8, we have 26. And as you can see, 26 is really the right child of 24. All right, we're going to find this formula is very useful when we come to insertion and deletion. The last formula that will also be useful later is that the index of the last non-leaf node, or the last parent if you like, can be obtained by dividing the count, where count is the number of elements in the tree, divide by 2 and then subtracting 1. So the index of the last parent, or the last non-leaf node, is count over 2 minus 1. Let's see, for example, here, how many elements do we have in this tree? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 elements. So according to this formula, the last parent is going to be at 10 slash 2, which is 5, minus 1. So 4. So the one at index 4, which is 31, is the last parent. Is that correct? You can see here, 13 is a parent because it has children. 21 also is a parent. 16 is a parent. 24 is a parent. 31 is a parent, but 19 is not a parent, it's a leaf node. Therefore, 31 is actually the last parent. Okay, after that, the rest will be leaf nodes. That's the idea of last parent. Okay, so if you are giving any tree, all you need to know is how many elements are there. If you know how many elements, then you automatically know the index of the last parent. We're going to need this index later for some of the operations. Right, so that is how to represent a tree, and these are the related formula based on this representation. We're going to use them later when implementing the operation of a binary heap. Okay, next is binary heap as a priority queue. All right, we learned about priority queue earlier in the course, and we learned that there are 2 different ways it can be implemented. Either you use sorted lists or unsorted lists. Either of these 2 approaches will require a kind of searching. For example, if you are using sorted lists, then when a new element comes, you must insert it at the correct place based on its priority. So the Enqueue has to be updated to do some searching to locate the correct place. Okay, we don't have to change the Dequeue in that case, just Dequeue the front element because the elements are sorted according to their priority. Whereas the other way, using unsorted list, when an element comes, just put it at the back When you want to dequeue, now you have to search. So again, there is a search involved. Now, we didn't implement priority queue when we look at lists, because as we know, searching in the case of lists is very inefficient because it's basically a linear search. So this is the and if you recall, at that time I said we will implement priority queue after we have learned a suitable data structure for implementing it. Well, this is the suitable data structure. It says here, binary heap is an excellent data structure for implementing a priority queue. We shall see the detail of the reason why, but I can just mention the two main important points here. One is that it allows direct access to the highest priority element. The highest priority element is always at the root. All right, so this is actually the point to note when deciding which of the two types of binary heap should you use. Should you use min heap or should you use max heap? You should use min heap if the highest priority element has the smallest value. For example, if you are trying to find who is number 1 in a particular race, and then who is number 2, and then who is number 3. So in that case, the smaller the number, the more the higher the priority. So in that case, min heap is the appropriate data structure to use, so that you will get the highest priority element at the root in position 0. On the other hand, suppose you are storing cities based on their population, and you want to give the highest priority to the city that has the most population. Then in that case, max heap is probably the most appropriate binary heap to use, because you will then be able to access the highest priority element at the root. Okay, so this gives you an idea when to use which one. And so the point we're making here is, if you consider any of the data structures we have seen so far, AVL and BST seems to be very good, for example, but can you get the smallest element or the maximum element directly? Clearly no, because the maximum element in AVL or BST will be the rightmost element. So you have to keep going to the right. The rightmost will be the biggest element. And similarly for the smallest element, it's going to be the leftmost. So it doesn't give you the biggest element or the smallest element directly. You have to search for it. Even though the searching is fast, definitely it cannot be as good as getting it directly. Just go to cell number 0 to get it. So this is one of the reasons. Now, this may not be a valid reason if insertion and deletion are going to be expensive. So this is why we have the second point here, that binary heap is an excellent data structure for implementing priority queue, not only because we can access the highest priority element directly, but also because insertion and deletion are as fast as BST or AVL tree, which are so far the best trees or the best data structures we have seen so far in terms of the efficiency of the insertion and deletion. So binary heap doesn't give you a worst performance in terms of insertion and deletion, yet it can give you the highest priority element directly. Therefore, overall, it is better to use it to implement priority queue even than using AVL tree, for example, or BST. All right, so this is the reason. Um, Now, to use a binary heap to implement priority queue, we need to be able to implement the two main operations of a priority queue, which are enqueue and dequeue. So we're going to see how we can do this, starting with enqueue. How do you enqueue an element in a binary heap? This is the algorithm. Of course, we want to do the enqueue such that the element we are enqueuing, it will go to the topmost position if it is the highest priority. And when you enqueue the element, it should go up the tree according to its priority. And this is the algorithm that will ensure we achieve that. So we have an algorithm here called heap enqueue. It receives an element, and it said the first thing you should do is put the element E1 at the end of the heap. Of course, this is the only place you can insert a new element in a complete tree. Remember, binary heap is a complete tree, and complete tree grows top to bottom, left to right. So if you want to add any new element, you have to go to the last level and put it to the right. If that level is full, then create a new level and put it to the left. Okay, so put the element E1 at the end of the heap. There is only one place you can insert a new element in a complete tree. Now, putting that element there, however, may violate the second property of a heap, which is the one regarding the ordering of the elements. So you have to restore the order using a loop. Say, while E1 is not in the root, while element is not in the root, and element is less than its parent. I should emphasize this algorithm is for a min heap. So for a min heap, we want the smallest element to go to the top. If you are doing it for a max heap, then this should change to greater than. Okay, so while element is not in the root and element is less than its parent, swap the element with its parent. Alright, if it is for max heap, while element is not in the root and element is greater than its parent, swap the element with its parent so that the bigger element go top. This is the idea. So this is the algorithm for enqueue. We're going to take examples to illustrate this to make sure you understand it well. But there is one terminology I need to introduce here. It says the process of swapping an element with its parent in order to restore the heap order property is called percolate up. Okay, so this loop is doing percolate up. To enqueue an element, you put it at the end of the tree and then you percolate it up. Percolate up means swapping it with its parent, as long as in the case of min heap, it is smaller than its parent, then the parent has to come down and the smaller one, will go up. And you keep repeating this until you reach until this condition is no longer the case, or until you reach the root. Let's see examples. This is our first example showing how to enqueue into a heap. So here again is a min heap. Okay, so how do we enqueue into a min heap? Suppose we want to insert 18 into this min heap. So according to the algorithm, first put the 18 at the very end of the tree, which means to the right of 31. This is the only place we can put a new element. If you put it to the left of 19 or right or anywhere else, the tree will no longer be complete, and that will violate property number 1. So the only place we can put 18 is here, to the right of 31. Okay, so we do that, create a new node and put 18 there, to the right of 31. Then now calculate 18 up until it reaches the correct place. How do you calculate? You will be comparing 18 with its parent. If you are dealing with min heap, then you should be checking if 18 is less than its parent, then the parent will come down and the smaller element will go up. So since this is a min heap, that's what we are going to do. 18 definitely is smaller than 31, so 31 will come down here to replace the 18, and 18 will go up to replace the 31. So the swapping, basically we are swapping the two elements. Okay, so this is step number 1. But you don't stop there. You again repeat, is 18 compared to its new parent, is it smaller? Yes, it is still smaller. So again swap, 21 will come down, 18 will go up. Okay, so 18 will come here. Again you ask, is 18 smaller than 13? This time it is not, and therefore this is where the calculate up will stop, and this is where 18 will be inserted. So basically this is the process of insertion. 2 steps. First, insert it at the end of the tree, then calculate it up until it reaches the correct place based on the ordering of the tree. Let's see another example, this time using max heap. And this example is from the book, figure 6.54. So this is our max heap. As you can see, the parent is always bigger or equal to the 2 children. I'm going to insert 15. So again, like the previous example, 15 has to be initially put here to the right of 7. Okay, so you have 15 to the right of 7. Then now you try to calculate it up. Now in the case of max heap, you will calculate up if the new element you are enqueuing is greater than the parent. So the opposite of min heap. For min heap is if it is smaller, because we want the smallest element to go to the top. Here we want the bigger element to go to the top. So 15 is bigger than 7, therefore 7 will come down and 15 will go up. And that's what you have. 15 has come here, 7 has come down. But again, don't stop. Compare 15 with the new parent. It is still bigger than 10. So 10 will come down, 15 will go up, the 2 will swap. Okay, but now again, if you compare 15 and 20, it is in the correct place. It is less than 20, so it cannot go top anymore. And this is the end of the enqueue. So this is how to do enqueue with heap. As you can observe, the enqueue process only goes through the level of the trees. Yani, in the process of calculate up, at most you have to do it h times, where h is the height of the tree. Okay, here we only did it 2 times. Okay, after inserting it here, we calculate it to come here, and then we calculate it to come here, and that is where it ended up. So in the worst case, we only have to do it h times. This calculate up process in the worst case must be repeated h times, where h is the height of the tree. Here the height of this tree is 1, 2, 3, 4. So you will not do more than 4 calculate ups to reach the correct place. So this is similar to the enqueue or the insertion process in BST or AVL, if you remember. Let's say AVL, which is balance, that one we are guaranteed is not going to be more than H. And remember, we keep going to the left or to the right until we find an empty slot. So again, the maximum number of searches we have to do is H, where H is the height of the tree. So this is why we were saying at the beginning that the enqueue process is as efficient as the enqueue process in BST or AVL. So this is why we decided that binary heap is a better data structure to use for implementing priority queue, because it doesn't incur any extra cost in terms of enqueue and dequeue, yet it gives you your highest priority element directly. Okay, now let's look at the dequeue, because this is another method we must implement if we are using a heap to implement priority queue. This is the algorithm for dequeue. It says first, now here again I should emphasize, we are dealing with a tree. So dequeue is very specific, not dequeue any element, no, dequeue the highest priority element, which in the case of binary heap is always at the root. So dequeue is very specific, delete the root and return it. Okay, it's not deleting any other element, delete the root. It's a queue, so we are always interested in dequeuing the front one, and the front element in the case of binary heap is actually in the root. So this is the algorithm. It says first extract the root element, usually save it in a variable, it will be returned later, but before that replace it with the element from the last leaf. As you recall, we said a binary heap, being a complete tree, can only increase at the bottom right. So it grows top to bottom, left, right. So there is only one place it can increase. Similarly, there is only one place it can reduce. The last element in the last level is the only one you can remove. So here it says replace the root with the last leaf, so meaning the last element in the last level, copy it and use it to replace the root. Then delete that last element, delete the last element, then calculate the root, because we have just removed the last element and put it at the top, so obviously the ordering of the element may have changed. So we have to restore the order. Okay, restore the heap order. So we're going to do the reverse of calculate up. We're going to do calculate down this time, because from the root, we're going to keep comparing that element with its two children and swap until it reaches the correct place. So we need a loop here. It says first, to do this calculate up process, initialize a variable p with the root, and then start a loop while p is not a leaf and p is greater than any of its two children. Okay, so if it is a leaf, we are done. But if it is not, then we know again, this is for min heap. If you want to do it for max heap, you have to replace this with less than. Okay, so if the parent is greater than the children, then this is not a min heap. We have to swap it with the two children. But which of the two? The smallest of them. So swap the parent with the smallest of the two children, and repeat the process. Okay, so until you make either this condition is no longer true, so we have reached the correct place, or until the new element we were trying to calculate down actually becomes a leaf. Okay, yeah, so this is the terminology again, similar to the calculate up for enqueue. We have calculate down. It's the process of swapping an element with one of its children in order to restore the heap order property is called calculate down. So again, this is best understood with examples. So let's take an example of dequeue using this min heap. Dequeue means delete the root, not any other element. Dequeue the root. So how do we dequeue the root? The algorithm says first extract the root. Okay, so like crossing it out, saving it the variable to be returned later. Next, copy the last leaf to replace it. So 31 will be put here in place of 13, and 31 will be deleted from where it is presently. Okay, so initially this is what you have. See, 31 has been deleted. It is now in the root. Okay, so obviously putting 31 here, which was at the bottom, has violated the min heap property. Now 31 is not less than its two children. So we have to restore the order. To restore the order, we will compare 31 against its two children and swap it with the smaller of the two. If it is max heap, we will swap with the larger of the two, because remember, we want the largest element to go to the top in that case. In the case of min heap, we want the smallest to go to the top. So here, 18 and 19, which is smaller, obviously 18 is smaller. So 18 will go to the top to be the new root, and 31 will come down. Okay, so this is what we have after one percolate down. But again, you don't stop there. Again, you look at your 31 against its new children. Is it still bigger? It is still bigger. Okay, so swap it with the smaller child. This time it is the right child that is smaller, not the left. See here it was smaller. It is the left one that was smaller. Here it is the right. So it doesn't matter the right or the left. We want to swap with the smaller child. So 21 will go up to replace the 31, and 31 will come down. Okay. But this time, if you check, 31 is actually smaller than its left child. It's only one child. So the percolate down will stop. Okay, so the percolate down will stop either as a result of reaching the correct place like here, or when we reach a leaf. Okay, because suppose this was 30, we still have to take it up and bring the 31 down, and then we will stop at that point because we have reached a leaf. So this is how to do dequeue. Let's take one more example, this time with a max heap. And again, this example is from the book, figure 6.65. We have a max heap and we want to dequeue. Dequeue means delete 20 and return it. So we extract the 20 and copy the last leaf to replace it. Which is the last leaf? Obviously 6. So copy 6 to replace the 20, and you will have this, and delete the 6 from where it is right now. So 7 becomes a leaf node because now it doesn't have any child. Okay, but this putting 6 here has violated the max heap ordering property. Now we have a parent smaller than the two children, which is not allowed. So we're going to percolate it down. Okay, and notice when we are percolating, this is our pivot. This is the element we are concerned with. Keep comparing it with its two children and swap until it reaches the correct place or until it becomes a leaf node. So here the swapping should be done with the larger of the two children because it is a max heap we are dealing with. Okay, so the two children 10 and 15, which is larger? 15 is larger. So 15 will go to replace the 6, and 6 will come down here. So this is what we have after step number 1. Again, you ask, is 6 smaller than the two children? Yes, it is. So the larger of them should be replaced with it, or should be used to swap with it. So 14 will go up, and 6 will come down. And now that it has become a leaf, the process will stop. Okay, so this is how to dequeue using max heap. Good. So it is easy therefore to implement priority queue using binary heap, and this is Java code showing you how you can implement this using Java. First of all, we define an interface for priority queue. So priority queue as an interface has three methods: enqueue, dequeue, and front element, or find front. Any class that implements these three methods is said to be a priority queue. It implements the priority queue interface. So we're going to implement min heap, not max heap. Max heap will be left for you to do as an exercise in the lab, but min heap will be implemented as an example. And this is our class for the min heap. So it's a class min heap, generic. However, the T that will be stored in the tree, like AVL and BST, must be comparable. Why? Because as you saw, there is an ordering property to be satisfied for min heap as well. The parent should always be less or equal to the two children. So how can you ensure that it is less or equal if the elements are not comparable? So that's why we put this restriction. Is generic T such that T is comparable. Okay. In addition to that, the class min heap implements priority queue interface. So we expect to see these three methods and some others implemented in the class. Okay, so that's the class heading. In terms of variable, there's only one variable, which is an array list. As we said, heap is generally implemented as an array. So here we have chosen to use array lists, which is actually an array. Okay, the constructor is doing nothing other than creating the array list, okay, as an empty one. Here is just declaring it, not yet created, but the constructor here is saying heap equal to new array list. So the array list has been created by the constructor. Okay, now how do we enqueue? So we need to have enqueue, find front, and dequeue. I will show you dequeue in a moment, but let's go through these ones first. Now enqueue is going to be exactly as we discussed it. And what it will do is it will put an element at the end. So here is the element to put. How do we make sure the element is put at the end of our array list? Just call the add method. By default, add will add at the end. So just say heap.add key. So the element has been placed at the end of the array list. Next is to calculate up to make sure the element is in the right place. So we need to take the index of the last element that we have just added. What will be the index of the last element? Is going to be the size of the heap minus 1. So we call the index whole, okay, because we're going to be swapping until we reach the correct whole where we will actually do the real insertion. So we take the index of the element we have just inserted. Its index is heap.size minus 1. And then we call a method called calculate up, starting from that index. We will see the method calculate up in the next slide. So this is all that enqueue is doing, exactly as in the algorithm. Put the element at the end and calculate it up. Okay. How about find front? Well, find front is always at the root, and root is having index 0. So to get it, just say return heap.get the element at 0. But of course, check that the heap is not empty. So if it's empty, return null. Otherwise, return heap.get at 0. Now the queue is also exactly as in the algorithm, except here there are two trivial cases to take care of. If the heap is empty, okay, perhaps we could have called it empty instead of checking if heap the size. If heap the size is 0, meaning the heap is empty, there is nothing to dequeue, just return null. Okay. Also, if there is only one element, so if heap.size is equal to 1, there is no calculate down needed, just remove. So heap.remove the element as 0 and return it, and we are done. Nothing else to do. But if there is more than one element, then in addition to removing and returning the element, we have to calculate down. So these are the steps. First, get the element at 0, save it in a variable called root. Okay, heap.get0, save it in root. Eventually, we will return it. Okay, remember the method is not void, it's returning the element that is being dequeued, which is the root. So get the root, okay, and eventually return it. But before returning it, the second step in the algorithm says we should copy the last leaf and use it to replace the root. So how do we do that? So here it says remove, heap.remove the last element. As we mentioned here, the index of the last element is actually heap.size minus 1. So if you give the remove method an index, it will remove the element, but also it will return it to you. So here we're saying remove the last element in the heap and save it for us as a variable last item. Now replace the root with this last item. How do we say replace? We use the set method. So heap.set the element at 0 with this last item. So basically the element that has just been removed will now be used to replace the root. Okay, and the last part of the algorithm is to calculate down. So again, there is a method calculate down which I will show you, which will restore the ordering property. The calculate down after the queue will always start from root, so we put 0 as the starting index. Okay, this is the Dequeue method. As you can see, the methods are really very similar to the algorithm that, the example that we have discussed. Okay, here are the two calculate methods, starting with the calculate up. If you remember the calculate up, it will be comparing the current element with the parent and bring the parent down if the parent is greater, because we want the smaller element to go to the top. So we get the element at the starting index, save it as key. Okay, then we will use a loop to locate the right place for it. That's why we are calling this variable hole. Okay, at the end we will store the key at that correct hole. So here actually, instead of constantly swapping, no, there is no need to swap, just rather bring the parent down. If you find that the parent is bigger, just bring it down and update the hole to be the index of the parent. This is what this loop is doing. It's a while hole is greater than 0. Okay, hole is not yet the root. And if you compare, there is a method I will show you called parent here. This actually will return the index of the parent of a node whose index is whole. What is the index of the parent? So if we know the index of the parent and we use get, it will give us the actual element, the parent element. So now compare the parent against the key. If you get positive, it means the parent is bigger. So if it is bigger, it has to come down. So to do that, you say heap.set the element at whole with the parent. So bring the parent and put it in whole. Then now update the whole to be the index of the parent and repeat the loop again. So you keep moving your whole up until you find the correct place to insert your key. So after the loop, either we have reached the root or we have reached a place where the parent is not greater. So we have reached the correct place. Either way, replace the element at the hole with the key. So this is the key that we really want to insert. So after getting the correct hole, now insert it. This is basically what calculate up is doing. The same like we saw with the examples. What about calculate down? Calculate down, we are looking at it from the top down. But this time we have more work to do because a parent has two children. So we have to find, first of all, which is the smaller child. Is it the left child or the right child? And then, is this left child smaller than the parent? If yes, then bring the element that we are trying to calculate it down, bring it down, and so on. So let's go through the algorithm. So this is our index to calculate down from, usually root. So this is initially 0. Okay. So the first thing to do is save the element at that index in a variable called temp. So heap.get the element at whole, save it in temp. Now repeat this loop. As long as left at whole, here left actually will give us the index of the left child. We will see some method which I will show in the next slide. Left, parent, and one other method I will show you. Okay, left, right, and the parent. They are actually giving the index based on the formulas we discussed earlier. If you remember, if we know the index of a child, we can know the index of its parent. And if we know the index of a parent, we can know the index of left or right. So these are exactly what this method are doing. I will show you those in the next slide. So here we are trying to make sure that this element that we are trying to calculate down is not a leaf node. If it is not a leaf node, it should have a left child. So how do we know it has a left child? Get the index of the left based on the formula and check if the value of that index is valid. It is valid if it is less than or equal to the heap size minus 1. If it is not less than that, then it means that there is no left child for this node, so we should not proceed. Okay, so here we are saying repeat as long as there is a left child. Good. So assuming there is a left child, get the index of that left child. Okay, save it as a variable min. So initially we are assuming the left child is the minimum, but we cannot be sure. We still have to compare it with the right child, and that is exactly what the next statement is saying. So it's saying if there is a right child, the same like we did here, if the index of the right child is less than or equal to heap size minus 1 min, is saying if there is a right child and that right child is less than the left child, the current min, remember the current min is the left child. So if there is a right child and the right child is less than the current minimum, then update the minimum to be the right child. Okay, so at this point, min is really the smaller of the two children. Okay, having found the smaller of the two children, next thing is to compare that with the parent and see whether we need to bring the parent down or not. So that's what this if statement is doing. It's saying if minimum child is less than the parent, then we're going to do the swapping. So it's saying if heap dot get minimum, so if the minimum child is less than the parent is temp, remember? So the left child or the minimum child, whether left or right, if it is less than the parent, then you have to bring the parent down. So copy the minimum to actually not copy the parent down, rather copy that minimum up to replace the parent. That's actually what we are doing. So copy the minimum using the set method to replace the parent. Okay, then update your parent to be the minimum. So whole will be the index of the minimum that we just copied up. So it's like we are coming down the tree. And then repeat. Go back to the beginning of the loop and repeat. So again, you check, is there still a left child? If there is, assume it is your minimum. But then check if there is a right child, is it smaller than the minimum? If yes, update the minimum. And then repeat the process. So we keep repeating this until we reach a situation where this condition is not true, in which case we'll break the loop. Okay, because here if the minimum child is not less than the parent, here we are saying break, so the loop will stop, and only at that point we will copy the parent to the correct hole. We have found the correct hole to put the parent, so copy it now here. Okay, so very similar to the examples that we've been doing manually. This calculate up is needed by the Enqueue, and calculate down is needed by Dequeue. Okay, these are the method I was referring to earlier. As you can see, they are exactly like the formulas we discussed before. Right, if you give it an index, it is saying what is the index of the right child. So assuming the parent is at I, what is the index of the right child? Simply 2i plus 2. Similarly, the left child is 2i plus 1. Okay, what if it is a child that you have? Its index, the index of the parent will be I minus 1 slash 2. And the last formula, which we will use later, we don't need it in the Enqueue and Dequeue. We're going to need it later when building a heap. Last parent is always the count, which you can get by calling heap.size slash 2 minus 1. Okay, so those are the important method in the mini heap